All right, so how you guys doing today? Doing okay? Oh, perfect. Thank you. All right, so let's start the chapter 2. Okay. So make sure you guys keep watching the YouTube videos on YouTube channel because I always upload all the lecture I do. So if you don't come to the lecture in class or if you don't have any chance, make sure you guys keep up with just watching the videos so you can follow the pace in the lecture. Okay? So in chapter 2, we start talking about some atomic theory here. So let's start talks about some atomic structure. Okay, so atomic structure here, we actually going to follow some Bohr's model. Okay. Here, that means you have some very dense material, like located at the center of your atom. We're going to call this nucleus. Okay? Nucleus. So it's in the center of the atom, and then you're going to have some particles are actually moving around the nucleus in this atom here. Those are the electrons. Those are electrons. Okay. So kind of funny thing about this atomic model is that if you look at this picture, most of the mass of the atom is like really highly dense at the center of the atom, meaning like 99.999% of your atom is actually empty space. Okay? So that's kind of a weird that you're looking at the atom. Most of the parts of your atom is actually empty space, but in the center and little bit of the electrons are taking very small portion of your atom. Okay? So meaning most of the part of your atom is the empty space. So if I am the nucleus right here, if you consider me as a nucleus at the center, the edge of the atomic radius or the side is the end of the Troy. Can you guys imagine that? So this is how far and how empty this atom is. So center around me from the all space of the Troy is empty, except me. And some tiny electrons around it. So this is the somewhat brief idea about what it looks like. Makes sense, right? Good, perfect. Right. So if that is the case, when you look at the nucleus, we find out later it's made of protons plus neutrons. So in early days in the science, scientists didn't know if it's really empty or how it composed in the space inside the atom and everything. They find out when they're shooting a lot of the alpha particle through the atom, they find the most part is empty, and also that the really high dense material can reflect that particle, which has to be positively charged. And then also find the one is zero charge. It's neutral in charge, so we call them protons when it's positively charged, and located in the nucleus. And when it's in the nucleus, but there's no form of charge or no charge at all, it's neutral, so we call neutrons over here. So you have some particle that is positive and some other particle is neutral, but in some, at the center, you have a really dense material that shows the positive charge. So meaning, to make this atom more stable, meaning it has to be neutral. So if you think about electrical charge in a space, you know what happened to these two, right? They're going to attract to each other because there's an electric charge following the Coulomb's law. So that is why if you only have a positive charge that makes this atom unstable, so they make some way to balance the charge so it can be neutral, so be more stable. So this is why they try to store the electrons around the nucleus that makes the whole atom over here. Okay, so this is kind of a Bohr's model because I kind of show you more like in an orbit kind of shape. So if you have more electrons and more electrons, meaning you're going to have a bigger and bigger atomic size, which will happen from top to the bottom in your periodic table. So if you look at the periodic table, if you look at the one vertical column, this is where you can see the similar, the elements that shows the similar chemical properties. So if you go from the top to the bottom, you can assume there'll be more and more electron that makes the more and more space for them to store more electron. That's why if you go from top to the bottom, you'll see the increase in the size of the atom or the elements. So atomic size will increase. Because of this, we're kind of following the Bohr's model that gives more and more to them. So this is a kind of so this is the charge. Does it make sense so far? We good? Okay. So if that is Bohr's model, but in modern physics, I don't know if you guys taking Gen Chem 2 or organic chemistry, but this is just the. Oh, I'm saying this is classical model that the Bohr suggested, but in modern physics, but this is a nucleus. You have actually sort of like a cloud, kind of like surrounding the nucleus, but it kind of fade out when you go from inner to the outside of the atomic model. So this is really like a dark and very kind of crowded cloud, where it kind of fade away from when it goes to the out and out, and we call this a cloud model. This is more like a modern model of the atom, meaning you don't have to always consider electrons only going to be around a certain orbit, but instead you can see this more as a cloud. So the darker cloud around the nucleus, close to the nucleus, is where you can find the electron by higher chance. So if you go from here to here, obviously this location is there will be very low chance to find the electron, but you definitely have a good chance to find the electron near nucleus. So it kind of makes sense that if you go out of the atomic size, there's 0% finding any electron over there. So this is kind of a bit of a more modern model of the atomic structure. Okay? So either way is fine. We're gonna use Bohr's model, cloud model, time to time, back and forth, for a certain application for the solving problem. But you just need to know there's some, classic model and modern model based on how we represent the electrons around the nucleus. That would be your atom. Okay? Makes sense? You good? Okay, perfect. So just keep this in your mind. Okay. All right. So today is the case. There are certain things I want to tell you. First one is atomic number. Atomic number. Okay. So atomic number is simply numbers of protons in your atom. Okay. So that is exactly how you arrange your elements in the periodic table. From top left, this is the hydrogen number 1. Hydrogen has only 1 protons. And if you go, so the way you read the periodic table is always start from the top left corner, which is the hydrogen, and you go left. So that is what? Helium, right in the corner, okay? So hydrogen, you go helium, right? And there is lithium here. So you go from left top corner to the right, and then you finish that the right corner, the far right column, and you go down and to the left to the right again. Okay. This is how you read the periodic table, and this is how you put 1, 1, 2, 3, 4, 5, 6, 7, 9, 10, so on. You put the numbers of protons, and that shows the atomic number. So what it really means is whenever you have a certain numbers of a proton, that defines that specific element. So for example, hydrogen has 1 proton, right? But somehow hydrogen gain 1 more proton into their nucleus. Then it's not hydrogen anymore. It becomes helium. So the atomic number is the same as numbers of proton in the nucleus, and that determines identity of the chemical elements. So for example, the carbon is number 6. You see the number 6 on the the carbon, right? In the periodic table, meaning carbon has 6 protons, but somehow carbon get 1 more proton into them. It's now nitrogen, not carbon, because that changed the identity of the chemical element. So the one that had 7 proton is nitrogen. So carbon somehow acquire 1 more proton into the nucleus. It becomes totally different element, which is what? Nitrogen. Makes sense, right? Okay, perfect. All right. So the other one is the atomic mass number. So this is simply, it's also pretty much just a number thing, but the numbers of protons plus numbers of neutron is the atomic mass number. So for example, you have a carbon 12, meaning your atomic mass number for this carbon is 12 because we know there will be 6 proton because it's a 6 on the periodic table. So we know by just looking at the periodic table. But if your atomic number is 12, which is right here, you normally put the atomic number on the top left corner of this chemical element symbol here. Then you know by automatically 6 plus 6 is 12. So you know there will be 6 neutrons there. So for example, if I give you carbon 13, once again, you cannot change this number. If you change this number, this is not carbon anymore. It could have been something else. But I said 13 as your atomic mass number on the top of the carbon means it changed only numbers of what? Neutron. So if that is carbon 13, unlike a carbon 12, it is going to be still same protons number, but 7 neutrons. Makes sense, right? Okay, perfect. So this is indeed happen a lot in the nature, in the universe. Meaning, even though there are certain elements that has the same number of proton, meaning they're same chemical elements, they're going to show you same chemical properties, but they may weigh differently because the numbers of neutrons may be different. Okay, so that is why we have they got the all right. So they got the. So whenever you have chemical elements that has the same numbers of proton, means the same chemical elements, but different numbers of neutron, we call them together isotopes. Meaning they are same chemical elements because they have the same numbers of proton. Okay? But with different numbers of neutrons. Okay? So, meaning carbon 12, carbon 13 are basically the same chemical elements still. It only shows different number, atomic number, meaning it's slightly heavier because that has 1 more neutron, which is 7, has a 6 over here. So here's the thing I want you to kind of remember, because whenever you take the exam or the quiz, I'll give you the periodic table. And the periodic table will say, obviously atomic number, and also atomic mass number as well. So you'll see the numbers on those, not atomic mass number, but you'll see the average, the atomic mass. Meaning, here's the thing. So keep these two in your mind, okay? And you'll see this number on your periodic table. So here's the thing. Do you guys like apple? You guys don't like apple? Or watermelon? I do like apple, but depends on what kind, right? If I ask you, what's the size of the apple? How are you gonna answer me? Maybe, your fist much, right? Something like here, right? Whatever the apple you like, it's usually around this big, right? So maybe you can say, oh, this apple is just about this much big, like, one or two, this much of the much. But maybe if I go to the Walmart or some of the grocery shop, and I find a particularly big apple like this, and I'm gonna go and ask you, I'm gonna tell you, oh, you lied to me. Because I found this apple is this big, you said the apple is this big, right? But they are still what? Same apple, but just different in size. Atomic isotopes is just like that. So whenever in your mind, think about it, in the people's mind, when they ask about certain matters of size, they always think about the average size. Even though you have this big apple, particularly by small chance, you're not going to tell me apple is this big, because most of the apple will be in this size. Makes sense, right? Okay, so meaning to tell me the average mass, atomic mass of the carbon, first thing what you need to know is the abundance, relative abundance. So if you have lots of carbons in 13 mass number, then you can say, oh, 13 is the average number of atomic mass will be close to the 13. If you do have a lot more of carbon 12, you're gonna say, oh, it's a slightly larger than 12, but close to 12, that would be your average atomic mass. So it depends on natural abundance. Which isotope is more abundant in nature, this is how we determine the average number for its atomic mass. Makes sense, right? Okay. So if that is the case, we can actually do it more in a precise way, because we can actually do the math on it. So this takes quite a bit of steps. So I'm going to tell you very slowly. Okay. Okay. So let's do these two. So let's just assume there are actually more of. So there's carbon 14 and some in the very raw chance, but let's assume there's only two isotopes just in case to make this question easier. So to make the average atomic number, which you can actually find it on the carbon, that is about 12.008 or something, but it's a very small number. But let's make it easier. So we can say it's carbon 12.1, just in case. If it is not, it's a lot lower number you see on the periodic table, but just in case that you find this number on your periodic table, okay? Oh, I forgot to tell you. So whenever we mentioning about the atomic mass or the molecular weight, we use either AMU or you can say gram per mole. This basically the same thing I'm gonna tell you. So AMU, so think about it. Whenever you have a 1 protons, right, or 1 neutron, that number is really, really small, right? You think about the 1 proton, 1 neutron is really, really, really small. That is like a 1.7 times 10 to the negative 27 kilogram. So if you want to use that small number in every calculation, will be too much of work, isn't it? Right? So we put it in the nicer way to put it. We multiply that number by Avogadro number we're going to cover soon. So let's just assume that 1 proton or 1 neutron is just about 1 AMU mass. Okay? So this is what we call as the 1 atomic mass unit. So this is almost same as similar concept as 1 gram per mole. So meaning if you have a 1 mole of the proton or neutron, it will weigh about 1 gram. Meaning 1 mole is the Avogadro number. Can you look at this number here? It's a really big number. See, 6.022 times 10 to 23rd. 23rd, meaning you're going to have a 0-digit number after this one 23 times. It's really big number. So if you can multiply the Avogadro number by its actual mass, then you'll get about 1 gram. So if you have this many proton or neutron, they'll weigh about 1 gram. So we're gonna put this either 1 gram per mole or 1 AMU. Either way is fine. So just the key point here, you don't have to know this. The key point here, we kind of consider each proton or neutron weigh about just 1 AMU or gram per mole, just 1. Makes sense, right? No question? Oh, perfect. So anyway, so the number you're actually going to see here is actually gram per mole or AMU. So this is something much easier integer numbers with, I mean, it's a little bit of fractional number, but here we can use for easier calculation. So to get this one here, let me here give you one example here. So if you have if there's a 100% natural abundance of carbon, either 12, 13, we assume there are only 2, right? No, we ignore the 14 is too small, maybe. Then maybe if you add 100% as a whole is 1, okay? I want you to do this because it just will be helpful for your calculation later. And then here's the thing: if your 1 is 100%, 0.5 will be a 50%. Sort of goes on. Like 0.1 will be 10% and so forth. Okay. Let's just assume this one. Okay, this is here. Then let's put your natural abundance of carbon-12 as x. Okay. Say your natural abundance carbon-12 is just x because it's unknown number, right? But if there's only 2 isotopes, for sure, this one has to be sum to be 1. Because we just assume that 1 is like a whole, like 100%. If you don't know how much you have on the carbon-12, so I just put x. But we know these two sum has to be 1. If there's only 2 isotopes, there are more. Or on your exam will be just, make it easier. So if there's only 2 major isotopes, x plus 1 minus x is 1. So whenever you assign this one as x, this is automatically 1 minus x. Because if you add these two, it has to be 1. So it doesn't matter. If you want to put this carbon-13x, you can do it. That's fine. You can put this as x, and this one as a 1 minus x. Doesn't matter. Doesn't matter. But I'm going to do this one in this way, okay? Okay? Alrighty. So if that is true, the average value that given to the exam of the question is actually much less than this number, but let's make it easier this way. So maybe this one. Then carbon-12 right here, carbon-13 is right here. And I'm going to use this number, your 12 as your atomic mass number, as your 12 carbon natural abundance calculation. So I'm going to multiply this one by x, okay? X. And then I'm going to multiply 13, they are the isotopes mass unit number. And I'm going to add those two, so it'll be 12 times x, because I assigned this one as x, and the 13 times 1 minus x, okay? And then it should give you average value of these two, that based on how much you have over here. And that is, once again, this is a number I made up, okay? Once again, this is we're gonna see different number there. But anyway, if that is this one, meaning, think about it. You wanna guess how much carbon-12 and 13 are there, but it gives you, the number is very close to 12. So even though we didn't do the calculation yet, which isotope do you think will be more abundant? That is close to 12. Will be 12, perfect. Because you have a larger carbon-12, so even though you have some carbon 13, the number you see as average is close to 12. That's why. So whenever you do the calculation, you can always double check, oh, I got the X value, but it's very small. But it has to be quite a big number to make this number close to 12. Then you can just proofread your calculation work again. So you can double check. But anyway, let's do this double check. Does it make sense so far? We're good? Okay. So anything is carbon 12X in here. So let's extend this one. So let's group this one with the one with the X, the one without X. Okay? This is what we can do. This is a 12 times X, simply 12X over here, right? 12X. And then this one will be going this way. Okay? 13 times 1, 13 times negative X. So that makes what? 13 minus 13x. Right? Because so you're going to add this one, and that has to be 12.1. Okay? 12.1. Okay? So let's try to do this one. So 12x minus 13x will be negative x, right? 12 minus 13 is 1, negative 1. So you group these two together. So 12x minus 13x plus 13 will be 1. But we know this will be negative x. Right? So meaning this one goes to, so now once this is positive in left side, if you move this one to the right side, what you have to do? You have to change the sign, right? Make sense? Okay. So that makes your negative x will be equal to 12.1 minus 13, which is negative 0.9. Right? So then just multiply negative x on both sides. Then you find out x is 0.9. Okay? And then only thing you have to do is multiply this number by 100%. Because you assume that 1 is 100%. You got 0.9 means you have to multiply this number by 100%, meaning you have 90% of carbon is 12. And that makes the other 10% of the carbon is what? 13. Because like I said, the carbon 12 is X. This is a natural abundance. Then carbon 13 was what? We said 1 minus X. So 1 minus 0.9 is 0.1. So if you multiply this number by 100%, that also tells you, oh, this means 10% of the carbon will be carbon 13. So meaning, if you go out there, try to find the one carbon elements, 90% chance will be carbon 12. And it will be 10% chance it will be carbon 13. That's what I mean by natural abundance. How much of each element, each isotope you can find in the nature by looking at the numbers of its average value of atomic mass. Make sense, right? Okay, good. Perfect. All right. Okay, then how about we just make another fake number here for carbon. Maybe I'll give you more example on next Wednesday because we don't have class on Monday. Okay. So anyway, so maybe I'll give you also fake number. If you find this average carbon value was maybe 12.8. Okay? So I'm sorry, it's a fake number, but I'm just giving you an idea how you can solve the problem anyway. So once again, in this case, this will be quite same. Only thing you have to do is try to put anything, one of them as x and the other as 1 minus x. It's always the same. And then, once again, it's between 12 and 13, but your average value is close to now 13 than 12. So even though you didn't do the calculation yet, you know that means you have a more numbers of carbon 13 in the nature. That's what it means. Okay? So in that case, you just need to do 12 times x plus 13 minus x. So it's pretty much the same, right? But you only change the number that is another fake number, which is close to the 13 at this time. So this is the 12.8. So it's pretty much the same. This is 12x, 13, negative 13x. So it gives the negative x plus 13 equal to 12.8. So now if you do this, that will become negative, right? So it will be negative 13. So negative x is negative 0.2. So now at this time that you have a different number for the average value, then this is going to be 20%. This is going to be 80%. Because this is negative 2, meaning positive x will be positive 0.2. So 0.2 times 100% is 20%. So that means you have about like a 1/5 chance you get a carbon 12 if every value is 12.8, and 4/5 chance you have a fairly good chance to find the carbon 13 in this case. Okay, makes sense, right? Perfect. All right. So if that is the case, let me introduce the maybe other things to do. So how about I'll give you about maybe 5 minutes because it takes quite a long time. Let's say you have a chlorine instead, okay? So let's assume there, I'm gonna also give you a fake number, okay? Don't worry about it, but the bottom is you have a 35 chlorine here, okay? And you have a 37 chlorine. And let's assume there's only 2 isotopes of chlorine. This the 35 and 37. So you can use them as an atomic mass number. And then maybe you find the number on the periodic table is about 35.50. Okay. So this is I also give a fake number here. And then could you possibly tell me what might be the natural abundance on these 2 in percentile units? It's the very same job you need to do, but switching the number those 2 in the carbon 12 13, and assign them one of them as x, 1 minus x, and put this number at the end, the other side, and solve for the x. Maybe 5 minutes I'll give you, okay, and then you can try it. Okay, about five minutes. Yeah, we'll do this together anyway. I just want you to try it out and see if you can sort it out with your own calculation work. That would be so great. But we'll do this again together anyway. But okay. Just maybe 3 more minutes. So it's so just assign one of them as x and multiply that by its atomic mass unit number, and the other one by 1 minus x, and that will be your this number. And so for the x, that's your number, and just multiply that number by 100 is that natural abundance of one isotope you choose as x in percentile units. Okay, maybe 2 more minutes. But it makes sense though, right? You good? Okay, yeah. Let's do this all together in 1 minute, and then we'll move on to the extra credit activities. Just 1 more minute. I know it's a kind of long step you need to follow, but this is the question that I cannot miss for exam. That's why I'm spending like a really long time on this one. This is the question you will see definitely 100% on the exam. So please make sure you guys know how to do this. You just need to follow the steps that they're giving you as an example of carbon. But you can also do with any other elements and isotopes as well. Okay. So if that is the case, I'll do the same pretty much. But let's try to do. I'll assign this one as x, and I'll assign this one as 1 minus x. Okay. And I'm gonna multiply these two, and I'll add them all. Okay. So 35 times x, and just group them there. And I'm gonna do this one too, 37 times 1 minus x, okay? And there will be 35.5, okay? This is the random number I made. And then just simple 35x, right? And then if you extend this one, it's just the plus 37, but it will be negative 37x, okay? So I'm gonna group these two together. So they will make 35x minus 37x, okay, and plus 37 should be equal to 35.5, okay. So if that is the case, this will make negative 2x, and then I'm gonna put this one in the other side, okay. So that makes negative 2 should be equal to 35.5 minus 37, because now it has to be negative on the other side. So that will give you a negative 2x will be equal to negative 1.5. So just multiply both sides by negative 1. That makes 2x should be equal to 1.5. So if you divide it all by 2, right, it will be x should be equal to 0.75. So once you get the number for x, once again, you just need to multiply it by 100, because we considered the 1 as 100% again. So that will make 75%. Okay? So in this case, you can assume if there's only 2 isotopes for that average number, this is going to be 75% abundance, and this is only 25% abundance in nature, in the universe. Meaning, if you go out there find 1 chlorine, 75% chance it will be 35 chlorine. 25% chance is 37 chlorine. Okay. So if you pick 4 chlorine, 3 of them will be 35. 1 will be 37 most likely, by chance. Okay. We good, right? Okay, perfect. All right. So, you guys doing so great so far? Very good. This is the isotope problem. We'll definitely do a little more maybe later, but you will see this one on the exam. So I'll just stop here today.